So let's think about the torque at the end doing the work, the end that's spinning. So let's draw our loop at some angle with some area vector like that sticking out, and it's in a uniform magnetic field B, and we know it has to be rotating at omega. So at this moment, the phi, the magnetic flux through the loop, is increasing. Because A is turning, I said it's turning this way, A is becoming more aligned with B, it's going to have its maximum flux once the area vector and the B field are aligned. So we can think about what's going to happen in this case. Well, we know Lenz's law wants to oppose the change. So Lenz's law wants to create a bigger flux the other way. Therefore, it wants to create a magnetic field the other way. So current is going to flow to make the field, to make a field back. So that would be current flowing, according to the right-hand rule, this way. So we're going to induce a current in this loop, is what really is going to happen. The direction actually doesn't matter. We're going to do the rest just with magnitudes. But let's note that the induced current feels a torque in the external magnetic field. So this thing is a current going around a loop. It has a torque, or it has a magnetic moment, IA, and it's in a B field. It'll feel a torque, just like everything we talked about in the earlier learning sequences. So that torque, it's actually in IA. So in means, I just drew one loop here, I could have in loops. It doesn't have to just be one. So the magnetic moment of a loop is in IA, just in case you have multiple loops. So we'll go ahead and write the in, just in case there's multiple loops in there. And then for the torque, it's that mu, this is basically mu, the magnitude of mu, crossed with B field. So we'll just write it as B, and then sine theta. Theta is the angle between them, but we know theta is omega t. So we'll write sine omega t. So that's how the torque will vary in time and with all the amplitudes. Now the power, we want to get from the torque to the power. So to turn it, we're having to overcome this torque. We're having to apply the opposite and push back. So the power that it takes to do that is actually omega, how fast we do it, times the torque we have to overcome. And the reason is similar if you want to think about pushing something in a straight line. You know, when you push, you apply a force along some path. The work you did was force integral of F dot dl, or just force times distance. The power you did depends on how fast you pushed. So you just take the distance per unit time, that's F times V. Right? So the power when you're pushing something steady is just the force times the velocity. Here it's similar. If we wanted the work we did to push against a torque, it would be the torque times the change in angle, times the sort of the how many radians we turned it. Or if you want the power, it's just that angle per unit time. So that's omega. Right? So power is torque times angular velocity. Okay, so now let's start plugging in and see if we can get the power. Let's see. So the power that we would have to do to make this happen is omega times NIA. Let's see, so N is just N. And then I, we're going to get from our previous work. So the current we calculated before, based on induction, was the EMF over the resistance. So the EMF was NBA omega sine omega t. That was the EMF divided by the resistance R, would be the current that you're going to have at any moment. And that's just I. Now we need AB sine omega t. AB sine omega t. All right, so let's put all that together, and we get that the power due to the mechanical work we're having to do is N squared, A squared, B squared, omega squared, sine squared, omega t all over the resistance R. And you can see that's the same thing. I kept it as we had here. N squared, B squared, A squared, omega squared, sin squared over R, over the load resistance. So it's true. If you're just turning a transformer against some load, if the load changes, the amount of power output changes, but also the amount of work you have to do changes. So there are many, 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 many more complicated transformers out there. I'm just showing you the basic AC transformer, just to give you the idea. We would have to do many, many courses to describe all the different transformers. Motors are sort of the same thing in reverse. With a motor, go to the other end and do some work on the electrical side, and you can produce a mechanical motion. All very similar equations. And then again, there are many, many different motors, so you can drive them with AC instead of DC. It's a whole world of information out there. But now that you have the basics, you'll be able to follow it.